This is our dedicated team, each contributing their unique skills and effort to bring this project to life.
Assalamualaikum and hi. Now, I will begin our group presentation. Our topic is about the kernel and range of a linear transformation. First, we will define both terms clearly and learn how to find the kernel using the equation TV equals to 0 or AX equals to 0. Then, we will go through some examples to better understand how these concepts work in real problems. We will also learn about rank and nullity and how they relate to the size of the domain. After that, we will discuss how to tell if a transformation is one-to-one or onto, based on the kernel and rank. And finally, we will see how to find a basis for both the kernel and range of a transformation.
Introduction of kernel.
So, what is the kernel? If we have a linear transformation T from V to W, then the kernel is the set of all vectors V in V that make TV equals to 0. So, this means that the transformation sends these vectors to the 0 vector. So, we will write it like this. In simple terms, the kernel shows us which inputs are lost or flattened to 0. Now, let's take a look at a simple example. Here we have a transformation T x, y, z equals to x, y, 0. This transformation takes a 3D vector and projects it into the xy plane. Notice that the z value becomes 0. So, any vector that lies along the z-axis like 0, 0, z will be sent to the 0 vector which is 0, 0, 0. This means the kernel of T is the set of all vectors on the z-axis. Let's take a look at the equation. So, this helps us understand how the kernel works in space. It tells us which directions are eliminated by the transformation. To end this part, it is important to know what the kernel is not just a set, it's a subspace of the domain V. That means the kernel follows the same rules as a vector space. It is closed under addition and scalar multiplication. So, when we find the kernel of a transformation, we are actually finding a subspace within the original domain.
Finding the kernel and basis.
Hello, let's quickly recap what it means to find the kernel of a matrix. The kernel of a matrix A is the set of all vectors X that satisfy Ax equal to 0. It also known as the null space and is formed a subspace of Rn, which includes the 0 vectors and closed under addition and scalar multiplication. To find the kernel of the matrix, we must follow this step. First, we set up the homogeneous system. Then, we reduce the matrix to row echelon form using Gaussian elimination. Next, we solve the simplified system to express the variable. From that, we write the general solution using free variables. Finally, we extract the basis for kernel from the general solution. Now, let's start using this example. Step 1. Set up the homogeneous system, which means Ax equal to 0. Step 2. Form the augmented matrix and reduce. Here, we start with augmented matrix and simplify it using row operation. After performing row operation, we get the matrix where the last row is all 0, indicating a free variable. Step 3. Back substitution to find solution. From the operation, we can write the system as x1 minus x3 equal to 0 and x2 plus x3 equal to 0. This means x1 equal to x3 and x2 equal to negative x3. Step 4. State the kernel and the basis. The kernel of A is the set of all vectors of the form T times vector, which 1, negative 1 and 1, where T is the real number. So the basis of the kernel is 1, negative 1 and 1.
Range, rank, and nullity.
Hi everyone, so now I will explain about the range, rank and nullity. So what is the range? Range is all possible output of a transformation. It shows what vector the transformation can produce. If range is the set of all, the formula is written as shown. So, if range equal to column space as dx equal to ax, so range T equal to column space of A. Means column space is all linear combination of A's column. So, to find it, firstly, row reduce the matrix to its row echelon form. Secondly, identify the pivot column, which is column fifth reading A1F. And thirdly, take the original column from that match those pivot position. So, how to find the basis for range? pivot columns for 1, 2, and 4, which is after row reduction. So take original column 1, 2, and 4 from A. So the basis for the range is 1, 2, negative 1, 0, 2, 1, 0, 0, and 1, 1, 0, 2. These vectors span the range and are linearly independent. So, what is rank and nullity? Rank is the number of independent output direction, nullity, number of input direction that go to 0, and domain is total number for input direction. So, rank show how much input reach the output, and nullity show how much get mapped to 0. So, from the theorem, the formula is written as rank T plus nullity T equal to domain, and all input vector either become output, which is rank, or get mapped to 0, which is nullity. For example, if domain equal to 5 and nullity equal to 3, the rank is 3, which is 5 minus 2 equal to 3, and the domain is rank plus nullity, which is 3 plus 2 equal to 5. So that's all. Thank you.
One-tune and onto transformations.
A transformation is one-to-one if every output comes from only one input. Theorem 6.6 tells us that T is one-to-one if kernel T equal to 0. In other words, the only solution to transformation V equals 0 is the 0 vector. A transformation is onto if its range covers the whole codomain. Theorem 6.7 says T is onto if rank T equals dimension W. If V and W have the same dimension, then transformation is one-to-one if and only if it is onto. In example 11, we apply these theorems to check whether a transformation is one-to-one, onto, or neither, just by checking the kernel and rank.
Okay guys, before we end our video, let's break it down step by step. First, the kernel is the set of input vector that gets sent to 0. They completely disappear, so it tells us what lost in the transformation. Next, the range is all the possible output the transformation can produce. It shows what's kept and where the input go. Then, we focus on two important ideas. First is rank is the number of dimensions that are preserved, the information that make it true. Second one is nullity is the number of dimensions that are lost, the part that get wiped out. After that, we look at special case. If only the 0 vector maps to 0, the transformation is one-to-one. If the transformation fills the entire codomain, it's onto. Finally, we tie it all together with this powerful formula. Rank plus nullity equal to dimension of the domain. This formula shows balance, how every transformation keeps some direction, loses other, and reshapes space in precise and predictable way. Now, let's bring this to the real world. Linear transformations are not just theory, guys. They are everywhere. They power 3D graphic in games and movie, fix error in your message, and simplify big data so we can understand it. So, whether you are gaming, testing, or doing data analysis, linear transformation are quietly doing the heavy lifting behind this. See how this connects to Islam. Islamic art use symmetry and geometry, all based on transformation. Qibla direction, found using coordinate math. Prayer time and hijri dates, calculate with precision using algebra. Even Islamic finance use math to stay fair and Sharia compliant. So yes, math is not just a number, it's beauty, direction, time, and justice in action.
Thank you for listening.